So now we have all the structure in place to be able to actually use calculus in polar coordinates. So we'll start out with the derivative. Since we write the radius as a function of the angle, right? We have r equals f theta. We plug in theta, we get an r, right? We also have the relationship with x and y. We have these relationships that x is r cosine theta, y is r sine theta. And so we use the formula that we came up with when we were talking about our derivatives in parametric equations to come up with dy, which is the derivative of r sine theta, over dx. And we treat r as a function, so we're going to have f of theta. So we go ahead and use the product rule here between r and sine theta and get the following. So we have f prime of theta sine theta, right, taking the derivative of r times sine of theta. And then we'll subtract here. Oops, this should be an addition, huh? We go ahead and take the derivative instead of the sine. We get the cosine, and we leave r alone. And so this is going to be our dy. On the bottom, we do the same thing, right? Except when we go to take the derivative of cosine, it becomes negative sine, and so we have a minus sign there. And so you can always just remember the derivative for parametric and just remember this kind of relationship, or you can just flat out remember this formula. But either way, we're going to go ahead and find the equation of the tangent line that intersects this particular curve we know as a circle, right, of radius 2 coming off of the pole and going to a spot 4 away on the x-axis. So I'll go ahead and make that curve here. Center at 2, going 4 away. That's almost a circle, right? um, and so we're looking for the equation of the tangent line intersecting this curve at the rectangular point 2, 2, which we know is going to be at the top of this circle. So say we didn't know how to make this curve, how would we go ahead and figure out the equation for this tangent line? Well, when we're looking at our derivative, which we obviously need for the slope of our tangent line, we have theta as our input. However, we're working with a rectangular point, which is again in x and y. So the first thing we have to do is take our rectangular point and express it as a polar point. And so we'll go ahead and say x squared plus y squared equals r squared. That'll give us one part of our polar point. And for our other, we've got tangent of theta is y over x. So we go ahead and have 4 plus 4 equals r squared. So r squared is 8, and thus r is going to be plus or minus 2 root 2. And then for our theta, that's inverse tangent then of y over x, which is 2 over 2. So inverse tangent of 1. And so we'll get pi fourths and all of its relations, right? We have the third quadrant sort of addition, which would be 5 pi fourths. And then for all of these, we add 2 pi n. And so we get our infinite number of thetas, right? And so we just want to pick kind of the simplest one, which would be using just pi fourths and just the positive r. Right, so that'll give us the point that we have to plug in once we figure out our derivative here. So we'll go ahead and figure out then. You might be wondering, since we are expressing r in terms of theta anyway, why would I bother finding what r is? The reason that I find that is so that I can pick the right theta and make sure that I'm being accurate with that. So we'll go ahead and find first dy. And then we've got r over dx. I'll go ahead and plug all this stuff in. We've got our formula up here. So we need to figure out r prime, and that's just going to be negative 4 sine theta. So we'll go ahead and plug that in. We've got negative 4 sine theta times sine theta plus, well, we got 4 cosine theta, so I guess we don't need the parentheses, 4 cosine theta times cosine theta over on the bottom here. negative 4 sine theta cosine theta minus 4 cosine theta sine theta. So on the top here, we've got 4 cosine squared of theta minus 4 sine squared of theta over, looks like negative 8 sine of theta cosine of theta. And using what we know about our double angle formulas, we can go ahead and express this. We can factor out a 4. We've got cosine squared of theta minus sine squared of theta. That's cosine of 2 theta. Over, we borrow a 2 from this, and now we have the double angle for sine. And by reducing here and writing an equivalence, we have negative cotangent of 2 theta. And so now it's simply a matter of plugging in theta. If we are evaluating this guy at pi fourths, we'll go ahead and write this over here, dy dx evaluated at theta equals pi over 4. We've got negative cotangent of 2 times pi over 4. That's negative cotangent of pi over 2, which is 0. And so now we have our slope. We use point slope. And in fact, we know this is going to be a horizontal line then if the slope is 0, so we can just have y equals whatever that coordinate is. And so we get our horizontal line, y equals 2. Right, so the derivative here is relatively simple and straightforward. And so we'll go ahead and move on to the next sort of bit of calculus, right? We're going to then move on to start looking at what happens if we start including integrals here. We'll first look at arc length. Now that we have a nice formula for our derivative, and we've kind of worked with taking r prime, we'll use r prime again in another situation. So remember that we do have the formula for arc length and parametric curves, and now we just have our parametric curve given in r and theta instead. And so for an arc length on alpha to beta, here's going to be our formula. We've got f of theta, remember that that's r. So essentially we can write this also as r squared plus r prime squared, if we wish, under a square root from alpha to beta. So either way, it should be the same thing. I think the book tends to go with this. So we have our original function squared plus the derivative of the function squared, take the square root, d theta. And so some important things that we kind of need to note here. First off, we haven't really dealt with a lot of functions that can go between positive and negative here so far, but really we have been kind of using the fact that this is the principal square root. Principal square root meaning there's no plus or minus up here. This is always positive. This is always positive. And so that's something that we need to note, especially since we're using trig functions more and more at this point. Whenever we kind of use trig identities and maybe somehow that square root can maybe cancel off, we have to remember that our integrand always needs to be positive. So for instance, if we end up with, say, something that looks like maybe this integral involving sine squared of theta under the square root, right? When we go ahead and cancel, right, really what should be happening is we should end up with the absolute value so we can make sure our integrand is always positive. And so sometimes we're actually going to have to split this integral into two different pieces depending on where exactly our sign is changing. And so that's something that we have to keep in mind because now we won't really have the luxury of just knowing that our integrand is always positive. So we're going to have to make sure that that's happening. Another thing that we have is we have a square root with two squared objects inside. This is definitely a right place for trig substitution. So look out for trig substitution. It can happen here, definitely. So we'll go ahead and take a look at a curve that we haven't really seen a whole lot of here, and talk about the integral necessary to find the length. So we're looking at r equals theta. So let's just think about what that guy will look like. All right, well, first off, when theta is 0, r is 0. So we've got that. And we'll go ahead and do this by, let's say, maybe pi halves. So this would be pi, negative pi. This would be like negative 3 pi halves, because our r should be equal to our theta. So what's happening is, as theta increases, r will increase as well. And so we'll end up with a shape that looks kind of like this, if I didn't miss. This is going to be a spiral, and it's just going to keep getting bigger and bigger and bigger and bigger. And so we want to find the arc length. How long is this spiral from this point all the way around to here? Right, and so the way that we'll do that is we use r. We have to also find r prime, which is just going to be 1 here. We'll go ahead and set up our integral. Our length should be from 0 to 2 pi. And we look at the square root then of r squared, which is theta squared, plus 1 squared, which is just 1. So this is the integral that we would utilize. And again, notice that we have theta squared plus 1, right? This isn't something that's going to yield very nicely to just regular u substitution. We're actually going to have to use a trig substitution if we want to evaluate something like this. So we would have to set up a triangle, and not only that, but our theta is already being used, right? We have the 2 legs here, so we would typically use what, theta here, 1 here, which means that our angle has to be something else. So I'll typically go with gamma. That's my go-to if theta is already spoken for. You can use like phi, psi, c, b, whatever you want that's not being used, but we can't use theta, it's already spoken for. So we would have to use trig substitution to actually evaluate this integral. We are not asked to in this particular problem, but this is definitely fair game. Right. The big meat of this this section, though, is going to talk about areas bounded by polar curves. That's going to be our main focus, at least. Those other bits are important, but we're going to talk definitely a lot more about areas either bounded by curves or even in between curves. So the way that we're going to kind of think about how our integral is going to break up, we can sort of take it from back here, right? If we're looking at arc length, then our bounds are values of theta. And remember, values of theta are rays that come from the pole. And so this is a graphical representation of kind of what that separation looks like. From theta going from alpha to beta, then we get these rays going out of our pole, right? So if f is continuous and non-negative, then we get this picture. So the bounding is actually going to be from the curve to the pole, bounded by our 2 rays coming out of the pole. And so all of our little sort of cross sections here, or sorry, our approximation shapes will actually be rays coming out, and our approximations will look like sectors of a circle. Right? So that is going to be kind of our method. Here I've got a left approximation. And so we use the formula for the area of a sector of a circle to make our approximation, and then we integrate by letting those letting the space between the sectors go to 0, or letting the number of sectors in this space go to infinity. So either way you want to look at that, when we go ahead and do that, we're not really going to use a Riemann-esque sum here. We're just going to jump straight into the integral. Here it is. So we've got 1/2, and then our r here, which is f of theta squared. So a relatively simple integrand compared to many of the things that we've done already, right? And so we'll go ahead and go from here and basically jump straight into what happens if we're looking between two curves. So if we've got two curves, f of theta and g of theta, where f of theta is further out from the pole. So we've got further from the pole, and we've got closer to the pole. That's going to be our situation where instead of looking top and bottom or right and left, we've got further from pole and closer to pole. So we'll have the further from the pole squared minus the closer to the pole squared. Stick a 1/2 on that integral from a to b. Right, and that's what our picture will look like. We've got, again, from the rays, alpha to beta there. Sorry, that's alpha and beta. And we're looking at the space from f of theta down to the pole in between these rays minus the space from g down to the poles. And that gives us the space in between the two curves. All right, so let's go ahead and take a look at an example here. So it says determine the inner loop of, and we've got r equals 2 plus 4 cosine of theta. Obviously, since we're asked to find an inner loop, we know that this should be a limison with a loop. So we'll go ahead and graph out what we're looking at here. So we start out with the midline at 2. And here's our midline here. And then we're looking at a regular period all the way up to 2 pi. So we got pi here, pi halves, and 3 pi halves. Cosine will start at the top. We've got an amplitude of 4, so we go up 4 from the midline. 1, 2, 3, 4, up here. Then we hit the midline. Then we go 4 down, which would be at -2 here. And then we go back up. So that's what we're looking for. So we'll go ahead and graph this guy at 0. We've got 6. 1, 2, 3, 4, 5, 6 out here. Let's see. At pi halves, we've got 2. And so we know in general what this shape should look like. We've got pi, -2. And so those are going to be the 5 points, right? We repeat this one that we get just from looking at these guys. Right, we typically like to look at what are these points here? What are the intercepts? So 2 plus 4 cosine of theta equals 0. We've got 4 cosine of theta equals -2. So cosine of theta equals -1/2. That happens, we'll just look at the first couple, right? That's what we're looking for in this first rotation. All right, so we're looking at pi thirds and 2 pi thirds, 4 pi thirds. And so that will give us the points where we are going to be hitting 0 here. So we'll go up and around. At 2 pi thirds, we'll kind of curve in. So I'll kind of do that backwards. We want to be tangent with this line when we hit this point. And likewise, the same thing. Oops, I've kind of made that too high. Or too low, I mean. We should be tangent with this line. There we go. And then tangent with this line as well. And then we'll go ahead and go inside here, hit our loop, back out, and then we'll just finish up this limison by making a nice, smooth, terrible looking, lumpy circle. There we go. It should be very circular looking, which is, that's pretty good. Not great down there. Let's try one more time, and then I won't waste any more time trying to draw. I think that was the worst of them, but there we go. So we're looking for just this little area in here. So on our curve, that's the point where we've gone through the pole and we're just looking at this space right in here, starting from this spot, going to this spot. And this then determines our bounds for our integral. So we're looking from 2 pi thirds to 4 pi thirds. We're looking at 1/2 and our function here squared. It's already a function of r, so we'll just go ahead and put that in there. Squared. So We'll go ahead and bring out that 1/2 probably. It's not necessarily very helpful. You know what? Actually, I'm seeing even numbers in here. Let's leave the 1/2 in. The issue that we're seeing is we are going to have to FOIL this, right? So we get, let's see, 16 cosine squared of theta. I'll go ahead and do that one first. Plus, multiply these guys together and then multiply it by 2. So we've got 8 cosine of theta, that's 16 cosine of theta. And then finally, square that last guy, 4. So it's a good thing that we left that 1/2. We'll go ahead and multiply that in. And so we get 8 cosine squared of theta plus 8 cosine of theta plus 2. And so this does also go back to where we were dealing with trigonometric integrals, right? We are going to have to do a power reducing formula on this guy. So we'll go ahead and start working with that. Or we'll have the 1/2, so this will end up being 4. And then we've got 1 plus cosine of 2 theta now. And really, I should be switching to brackets. All right, so there we go. I'll go ahead and multiply this 4 in. 2 pi thirds to 4 pi thirds. And then we've got 4 plus 4 cosine of 2 theta plus 8 cosine of theta plus 2. And so we'll go ahead and add up our like terms, and then we're going to be just about ready to integrate. We've got 4 cosine of 2 theta plus 8 cosine of theta plus 6 d theta. So we'll go ahead and integrate. We're going to, remember, divide by 2 here. We've got 4 sine of 2 theta over 2. And remember, if we're integrating cosine, we don't have to change the sign with a g. Plus 8 sine of theta plus 6 theta. And now we're going to evaluate this from 2 pi thirds to 4 pi thirds. All right, got some cancellation. This is now 2 sine of 2 theta. So go ahead and open up some brackets. We've got 2 sine of, let's see, 8 pi thirds plus 8 sine of 4 pi thirds plus 6 times 4 pi thirds minus 2 times the sine of 4 pi thirds plus 8 sine of 2 pi thirds plus 6 times 2 pi thirds. There we go. So let's see. We've got cancellation here. We've got 2 times 4 pi. Cancellation here, 2 times 2 pi. And then we need to evaluate. Right? Pi thirds is the one that doesn't play as nice. We get the root 3 over 2 situation. So we do have a very consistent, though. All of these are going to be root 3 over 2. We just have to determine, are they plus or minus? So we figure out what quadrant 8 pi thirds is in. Well, it's 6 pi thirds is a full rotation, and then an extra 2 pi thirds. So this is going to be in quadrant 2, which means that this guy is positive. We got 2 times root 3 over 2. 4 pi thirds, that's definitely in quadrant 3. So we've got 8 times negative root 3 over 2 plus 8 pi minus, again, 4 pi thirds is negative. So I'll go ahead and indicate that. So we've got 2 times negative root 3 over 2. 2 pi thirds is positive, right? Quadrant 2, so 8 times root 3 over 2 plus 4 pi. So we got root 3 minus, let's see, 4 root 3 plus 8 pi minus negative root 3 plus 4 root 3 plus 4 pi. Okay, and then we'll go ahead and distribute our negative. So we've got plus root 3 minus 4 root 3 minus 4 pi. And then go ahead and combine all of our like terms here. Let's see, we've got negative 3 root 3, negative 2 root 3, negative 6 root 3. And then we've got 8 pi minus 4 pi, that's plus 4 pi. So we got, I'll switch that order around just so we have the negative last. And so this is going to be our area. So if we had units, this would be square units. But here is our answer, right in there. Right, so this is going to be a nice combination of a lot of different techniques that we've looked at as far as we've got our arc length uses maybe trig substitution, and our areas will use a lot of trig integrals. All right, so let's go ahead and look at an example where we've got multiple curves and we're trying to figure out then a specific area related to these guys. So there's going to be lots of different areas, right? We've got this one in here, we've got this one in here, we've got this one out here. And so we want to determine which one we're really looking at here. So this says determine the area that lies inside 3 plus 2 sine theta. Remember, that's going to be a limison. And outside r equals 2, that's a circle. Right, that addition where we have a, well, just addition, where we have sine of theta with a coefficient plus some other number, that's our limison. This one is not going to have a loop on it, right? We think about what this graph looks like if we graph r versus theta, and we're going to be up entirely over the axis. We're not going to go negative at all. Right, and then we have our outside the circle there. So that's going to be inside limison, outside the circle, that's area 3 here. So we'll go ahead and determine a few things. First, we have to determine how do we start and stop our theta. We are intersecting at these two spots. We have to determine where theta is going to give us those spots. So we'll set it up just like we would set up any other sort of intersection argument. We'll go ahead and set these guys equal to each other and then solve for theta. So I get the sine of theta is negative 1/2. And so theta is going to be, well, we've got 7 pi 6 and 11 pi 6. Okay, but we think about how do we make this graph. 7 pi 6 to 11 pi 6 would be from here to here. But we want to go the other way. So the easiest way to do that is to say, this is 7 pi 6. Sure, we'll have this at 7 pi 6 and whatever our radius is. But instead of thinking this as 11 pi 6, why don't we think of this as negative pi 6 instead? That way, as our theta increases, we go to 0, go up to pi halves, all the way down to 7 pi 6. And so that's how we'll kind of modify things, and that way we make sure that we're just going straight from one theta to the next. So we'll go ahead and start at negative pi 6, go to 11 pi 6, sorry, 7 pi 6. 7 pi 6. And we've got 1/2. And now we have to determine which is our outside, which is our inside. Well, clearly our limison is outside, so we'll go ahead and take that guy and square it first, then subtract, and then we've got our inside will be our circle. And so this is going to be a very similar process to the last one, right? We're going to get a lot of this kind of thing. If we're dealing with any limison or a circle that's kind of hanging on to the pole and some number outside there, we're going to end up having to square our trig function, and we're going to have to use power reducing to bring it back down. In this case, I don't have all even numbers, so that 1/2 won't necessarily be very helpful to multiply in. I'll go ahead and take it out. And then we've got, let's see, 4 sine squared of theta. 3 times 2 is 6 sine of theta, and then multiplied by 2, we get 12 sine of theta, plus 9 minus 4. And so we combine like terms. Just get those constants together. We've got 4 sine squared of theta plus 12 sine of theta plus 5 inside our integral there. And so again, we're going to have to utilize power reducing. This time, we'll have a mixture of sines and cosines inside our integrand. But we get 2, 1 minus cosine of 2 theta. If we multiply by 1/2 there, our 4 turns into a 2. Plus 12 sine of theta plus 5 d theta. So we'll multiply out this 2 here and combine some like terms. So when we do that, I'll go ahead and put the sign up front now because we're about to have a negative 2 cosine of 2 theta. Then we got 2 plus 5, so our last term is plus 7. And so we'll go ahead and integrate. And we haven't started evaluating yet, so I'll leave that the way it is. We've got negative 12 cosine of theta, right? If we were to do that derivative, we get negative on the negative, we get a positive sign, right? So that works. Minus, we take the 2, divide by 2, we get sine of 2 theta. And then plus 7 theta. And we're now going to evaluate this from negative pi over 6 to 7 pi over 6. And so let's work that out. We got 1/2. Open up our brackets here. Open up parentheses. We'll plug in 7 pi 6. Negative 12 cosine 7 pi 6. And remember that 7 pi 6 is going to be in the third quadrant. We've already got that established. Minus sine of, but here's an issue. We've got 14 pi 6 here, which is going to be 7 pi thirds. Right, think about 7 pi thirds. That's going to be one full rotation is 6 pi thirds and then an extra. So this is in quadrant 1. Plus 7 times 7 pi over 6 minus negative 12 cosine of negative pi 6 minus sine of 2 times negative pi 6 is negative pi thirds. And then plus 7 times negative pi over 6. So we get 1/2. And then let's see what we get in here. Right, again, the cosine of pi 6 does not necessarily play very nice. We are going to get a negative, so negative 12 times, let's see, root 3 over 2, and 7 pi 6, we get a negative. Minus, the sine in pi thirds don't necessarily play nice either, so we get root 3 over 2 also. It should be positive, but we have a negative sign up front. Then plus 49 pi over 6. Okay, minus negative 12 times, and remember cosine is even, so we can essentially treat this as positive pi 6. So root 3 over 2 there. Sine is odd, so we can go ahead and take that negative out, turn it into a plus. Root 3 over 2. And finally, minus 7 pi over 6. So 1/2. And we'll go ahead and simplify here. We've got, I think I'm still going to need this bracket. Yeah. We've got 6 root 3 minus root 3 over 2 plus 49 pi over 6 minus negative 6 root 3 plus root 3 over 2 minus 7 pi over 6. Let's go ahead and distribute the negative, and we can start combining our terms here. So we've got 6 root 3 minus root 3 over 2 plus 49 pi over 6 plus 6 root 3 minus root 3 over 2 plus 7 pi over 6. And we didn't need the brackets anymore, so I'll go ahead and get rid of them, turn them in parentheses. All right, and so we'll combine like terms here. We've got 1/2 times 12 root 3, and these negatives turn into a minus root 3, and then plus 56, I think we're talking about here. Pi 6. All right, and then let's see, we've got 11 root 3 plus 56 pi over 6. So we've got 11 root 3 if we multiply in that 1/2 over 2 plus divide 56 by 2, we get 28 pi over 6, but we actually could reduce this further. So we'll go ahead and do that too. So 14 pi thirds. So 11 root 3 over 2 plus 14 pi thirds, and this will be square units. All right, so that was this area out here. So we'll continue on with the same kind of process here. And this one says set up the necessary integrals. So this one actually said determine the area. This one just says to set it up. To determine the area of the region outside of the limison, inside the circle. So we are talking about that guy in there. And so remember that our intersection we found by setting them equal to each other here. We got 2 sine of theta equals -1, sine of theta equals -1/2, and we set it up to be theta is 7 pi 6 and 11 pi 6. In this case, if we look at how does theta change from 7 pi 6 to 11 pi 6, that is actually this little space in here. So those are the bounds that we want to use. And so we've got 7 pi 6 here, 11 pi 6 here, and we've got 1/2. Our outside function is now the circle. So we'll go ahead and put the circle there squared, minus the inside function is going to be our limison. All right, so this is the integral all set up. So this is our answer to this particular problem. The actual integration is almost a carbon copy of the last one. There's just a few key differences, right? We're plugging in something slightly different, and we have a negative here instead of the other way around. So if we were to do that all out, it would look very similar. We would end up with 7 pi over 3 with a negative on that, plus 11 root 3 over 2, right? So very similar to our previous answer here. All right, and so the last one, set up the necessary integrals to determine the area inside both. So inside both, it means it's got to be inside here. All right, so the best way to set up this integral, this is a little bit trickier, right? Because part of it we're inside the circle and there's just the pole there. Part of it we're inside the limison and there's just the pole there, but we have to decide when does that happen, right? So again, we have that this guy over here is 7 pi over 6. This guy here is 11 pi over 6. And so the best kind of setup that we're actually going to be able to do here is instead of kind of splitting it up into 2 separate integrals and working with it that way, in this particular situation, since we have a circle, what we want to do is we want to use the area of a circle and then minus the area from this guy here, right, which is the previous example. So minus the area from the previous example. That's going to be the best way to set up this integral. So a equals pi r squared, pi times 2 squared, that's the area of the circle, and the red guy in there, minus the same integral that we had previous to this. So instead of messing around with those multiple integrals, this will be our integral. Right, and again, you know, it's just taking pi r squared here and subtracting what we got before, right? So it would end up being 4 pi minus negative 7 pi over 3 plus 11 root 3 over 2, right? If we were to use the previous example there. And so we get 4 pi plus 7 pi over 3 minus 11 root 3 over 2. This is 12 pi thirds plus 7 pi thirds minus 11 root 3 over 2. And so our final answer here, we would get 19 pi thirds minus 11 root 3 over 2. Again, this problem wasn't actually asking for us to evaluate the integral, just to set it up, but there we go. All right, so now we have a rose curve, right? 2 cosine of 2 theta, right? We have that altered period here, which means we're going to have some sort of rose curve. And we have a 2 out front that gives us the length of each petal. So it says plot the point that corresponds to theta equals 3 pi halves. State the interval on which the shaded area lies, and then find the area of the shaded region. So this is a very standard type of problem. Find the area of a loop of a rose curve. Find the area of a leaf of a rose curve. They're all kind of the same problem stated in different ways. But first off, let's go ahead and plot this point. We've got theta equals 3 pi over 2. So f of 3 pi over 2 is 2 cosine of 2 times 3 pi over 2. That's 2 cosine of 3 pi. That's negative 2, right? Negative 1 times 2. And so when we go to 3 pi halves, then we go around this way down to 3 pi halves. Negative 2, we go up through the pole up here. So this is negative 2, 3 pi over 2. Remember that our points are given as r theta. Okay, so that's the point. Next it says state the interval on which the shaded area lies. So we are going to have to graph r versus theta, which is relatively simple since we don't have any shifted midlines or anything like that. Amplitude is 2, so we'll go up 2 and down 2 just from the axis instead. What is different though is we do have that altered period. So we'll still go, remember, up to 2 pi, we have to graph the entire curve. And remember from last section, the entire curve is graphed when we have a multiple of both 2 pi and the period. The period here is 2 pi over 2, which is just pi. So the multiple that works to graph the entire curve is a multiple of pi and a multiple of 2 pi. That's just 2 pi. But that being said, we're going to need to break up our we have one period here, so we need all of our points sort of represented here. We've got pi over 4 then that we're going to have to graph out. So we've got 2 pi here, we're going to have 3 pi halves here, and we need those midpoints as well here. Right, so we've got 5 pi over 4 and 7 pi over 4. And we'll go ahead and graph this as the cosine, which means it starts at the top, goes through the midline, then the bottom, midline, top, midline, bottom, midline, top. I'll try my very best. That's not bad. There we go. So now we need to figure out which of these corresponds with this guy down here. Right, well, we know that we're going from theta equals 0 to theta equals pi fourths. That's a positive r, which means that this is the top half of the right petal. And which means that this is the other half, right? We've got 7 pi fourths to 2 pi, and we're, again, positive. So we're looking at, this is the bottom half of the right petal. So we'll also figure out this other area where our r is positive. We're going from 3 pi fourths through pi to 5 pi fourths. Right, this region, 3 pi fourths to 5 pi fourths, is going to be here. And r is positive, so we know then that this is the left petal, this section in here. And so we know that this section is either the top or the bottom, this section is either the top or the bottom. But we also have seen theta equals 3 pi halves is this point up here. So that means that this has to be the top petal. And so this area in here is what we're looking for. This is the bottom petal. So we're looking at our theta is going to be in this little region here, pi over 4 to 3 pi over 4. So that's where our integral is going to be set up. We've got a equals integral of pi fourths to 3 pi fourths. And the thing with rose petals is that these are all symmetrical when we're sort of considering ray from the pole, right? This bottom half and the top half are symmetrical to each other about this line. So our petal is going to be symmetrical. Right, we can go ahead and just break it up here instead. So this is a good strategy. There's a lot of symmetry when it comes to a lot of these curves. So you want to use that to your advantage. So instead of looking at pi fourths to 3 pi fourths, since we're looking at a symmetrical petal, we can go ahead and just say 2 times, and then we'll go from maybe pi fourths to pi halves. Because, you know, pi halves is going to work out a lot nicer. We like plugging that in to our trig functions, right? So we'll go ahead and work with that. And then we've got 1/2 2 cosine of 2 theta. That's our r. We'll square that. Oops. Put that square in the right place. And so another nice thing that we see here is the 2 and the 1/2 will cancel. There we go. So we go from pi fourths to pi halves. We've got, let's see, 4 cosine squared of 2 theta d theta. And so we'll work this up here. I've got just a picture of the rose curve, but we've kind of taken care of that here. So we'll go ahead and do power reducing. So we'll bring out the 1/2 here, and it'll cancel a little bit with the 4. We get 2. And then we get 1 plus cosine of, we already have 2 theta. We need to multiply that by 2 and get 4 theta now. D theta. We'll bring that 2 out front. It's not really going to be very helpful to us from now on. And we've got cosine of 4 theta plus 1 d theta. So we'll go ahead and integrate. We get sine of 4 theta over 4, right? We always have to divide by that guy, and this time we don't really have anything out here to cancel with, plus theta. We're going to evaluate from pi over 4 to pi over 2. All right, so we'll go ahead and do that. We get, first off, the sine of, well, we're going to plug in pi halves first. We multiply it by 4, we get 2 pi in here, plus pi over 2, minus, and then we've got the sine of pi over 4, plus pi over 4. All right, so we've got 2 times, well, sine of 2 pi is 0, so we got pi halves. And then here we've got sine of pi is also 0, so minus pi fourths. So 2 times pi halves minus pi fourths is pi fourths. And so we get pi over 2 square units. And that's going to end off this particular section. And that's actually then the end of the material that we'll be covering in this class. So it's been fun. Thank you guys for working hard this semester, and we'll have our final review coming up here, and I'll hopefully talk to you guys there.